graphical display, and I know from the part number, because I've used these type of displays before, it's 160 pixels by 128. And although this display is bluish in color, that's all it can display. It can display like a light blue or a dark blue, or a white or a blue, what they call it. So when the pixel's on, it looks white, and when it's off, it's blue. So each pixel can only be two colors, well, on or off, white or blue. But there's 160 pixels by 128. So 160 across, 128 down. So that, and each one of those, to store the memory for those, 1 bit again too. But it's 160 times 128. Mark these up. 160 times 128. So this is 20,480 bits for the whole screen. Right? And if we divide that by 8, it's 2,560 bytes. This display required 4 bytes. This one requires 2,560. A significant number more of a significant amount of memory more. Okay, now this one, this color display here, it's a 240 by 400 RGB display. And RGB stands for red, green, blue. And it doesn't indicate how many shades of each color. Let's say there was 4 shades of each color, red, green, and blue. So that would mean you have 240 bits wide times 400 bits hot pixels, 240 pixels wide by 400 pixels high, and then times 4 bits for red, times 4 bits for green, and times 4 bits for blue. So this one requires 6 million bits, 6,144 bits, and then we'll divide that by 8. So that's 768,000 bytes. So not quite a megabit, but 768 kilobits. Now this display, requires so much memory that the chips that we're using in this class, some of them have 512K of program space and 128K of RAM. So if you used all of the program space and all of the RAM, you couldn't even store a single image for this display on this processor. Now, what you might be able to do is draw a line. This display may have memory built into it, so you may be able to draw to it and draw lines and higher level shapes to be able to still use it with this type of processor. But you couldn't store the images for this display on the processor. And you could use external memory like a SD card. This display, black and yellow display, and this display, they're a special type of display that are graphical, but they have built-in fonts, so you're only sending ASCII characters to it. So this one might be like a 40 by 4, so maybe 40 characters across and 4 lines down. And then, so it would be 40 times 4, it would be 160, and then each character would be an ASCII character, so times 8 bits, so 1K for this whole display. If you actually had to store the individual pixels, it would be quite a bit more. And each little pixel here it's 5 pixels wide by 8 pixels high. So if it did it per pixel, it'd be 5 times 8 times 40 wide times 4 high would be 6,400 bits or 800 bytes. But just store ASCII 40 times 4 times 8. Divided by 8, actually, that's the number of bits. It'd be 160 bytes, right? So if we stored all the individual pixels, it'd be 1,000 something bytes, but if we just store the ASCII characters, it would be 160 bytes. They allow us to put a lot of information up without having to deal with the complexities of the display. So the display we're using looks a lot like this, where we have this, it doesn't look a lot like this. It's exactly like this, right? We have digit 1, 2, and 3. There's 3 7 segments, a decimal point 1 and a decimal point 2, and the segments are labeled A, B, C, D, E, F, and G in the center. And each display segment is identical to the ABC pattern is the same. And if you get a 7-segment LED, it's also the same. They label them the same on a 7-segment LED. Besides the pixels, there's a backplane. So these displays are called liquid crystal displays, and the way they work is there's a crystal that's suspended in liquid that when you apply a current to it, the crystal will twist, and when it twists, it will block a certain polarity of light, and then the top of the display has another polarized piece of glass. So I guess, I'm talking about light polarity, and a lot of you may not even realize that light has polarity. So polarized light, the wavelength of the light could be oscillating up and down this way or this way. And there's certain types of glass that will allow a particular orientation of light to pass through and block other orientations. Like polarized sunglasses, exactly like polarized sunglasses. And if you ever looked at an LCD display with polarized sunglasses, they look black, right? And the reason why is because, and if you twist your head, sometimes you could see it, right? And the reason why is because if your lenses are polarized this way and the LCD is polarized this way, the polarized light coming through the display and hitting your glasses is blocked. So the light comes out of the display like this, hits your glasses, and it's blocked. But when you turn your head, your glasses are in line with the polarity of the display, and now the light can get into your glasses. Okay, so in order to cause these crystals to twist, if you pass a current through them, it will cause them to twist. And when they twist, the polarity of the crystal changes. The interesting thing about it, though, is because these crystals are suspended in liquid, it's a liquid crystal display, right? And they are affected by current flowing through them. The current, if it always is flowing in the same direction, the crystals will actually start to migrate. They'll try to move. And the problem with that is that the segments will start to blur. It doesn't happen immediately, but if you did this for several minutes, and I mention this because as you're working on things on this lab, people will freak out because they're like, I got DC on my display, right? It's not actually oscillating. And when that happens, it won't ruin the display instantly. It takes a couple of minutes. And if it does happen, they just get blurred. And these displays, if you're really that concerned, they're only about $1.50, right? So they're not really expensive. So it's not like you're ruining a very expensive thing. And once they become blurry, they're still usable. They just get a little blurry. The way you keep them from getting blurry, though, and the way that the displays work, is the whole back of the display is connected to either a plus voltage or a negative voltage. Individual pixels are connected to the opposite voltage. So if the back plane is 0 volts, and you connect a particular pixel to 3.3 volts, it'll cause the crystal to twist and it'll become dark. But the opposite is true. So if the backplane is 3.3 volts and the crystal is 0 volts, the crystal will twist and it'll become dark. If they're the same voltage, so if the voltages are different, it'll twist. If they're the same voltages, it won't. And so if the backplane is 0 volts and the individual element is 0 volts, it will be off, and you won't see the segment on. So in order to turn the segments on and off, you just need to make sure that whatever the pixel is a different voltage than the backplane. And it sounds complicated, but actually the library that's provided does that already for us, so we don't have to think about it. All we have to do is think about which segments we want to turn on, and then there's a command that says refresh the display. And every time you refresh the display, it flips the polarity for you automatically. And it's easy to flip the polarity because we just invert everything. We invert the backplane voltage, we invert the bits every time. Right? And that puts the AC on the display. Okay. So in order to turn on the displays the way we want to, we're going to do what's called bit mapping, where we're going to create some bits that represent the segments we want to turn on. And the example here shows the number 4, right? So if we want to display the number 4, we want to turn on segments B, C, F, and G. And we're going to store this in a table, and then when we'll be able to call a function that will look up the value in the table and turn the proper bits on the 7 segment. And the way the table is going to work is like this. So if we have the number 4, and we want to turn on the segments B, C, G, and F, what we're going to do is in the B, C, F, and G positions, we're going to put the number 1, and in the other positions, we're going to put a 0. So 1's going to represent segment on, 0 is going to represent segment off. And then we're going to convert this value to hexadecimal, which is 66. So 01106, 01106. And this last bit, so it's only 7 segments, A, B, C, D, E, F, G, but this last bit we're going to be able to use for either decimal point 1 if you're on digit 1, decimal point 2 if you're on digit 2, or if you're on digit 3, it's going to be the backplane. So we'll be able to control the backplane voltage by setting the 8th bit for digit 3. Alright. The way the 7-segment display works is every one of these segments goes to a pin, and the backplane goes to a pin. So we got 3 times 7's 21, 22, 23, and the backplane is 24. So the 7-segment display has 24 pins, where 1 pin is the backplane, and the other 23 pins are the individual segments. Now, if you take the display out, it should have come in your kit in some ESD foam. The amount of energy required to cause those crystals to twist is very low. So when you take it out of the foam and you hold it in your hand, you'll see that the segments will just light up. It requires very little current to keep those lit. It draws very little current, so they're very high impedance devices. And the nice thing about that is they're very ideal for portable applications where you want to minimize the battery. Turn those segments on is we're going to use shift registers. If you've had digital, or if you're taking digital now and you've gotten to the lab, there's a lab on shift registers. This is a shift register that has a buffered output. So if you don't recall, the way shift register works is we're going to take some serial data, and it's going to be this pin SER. And the serial data will come in and be sitting on this D flip-flop.